we always have to differentiate between blow down and blow off. And that's because the ASME differentiates. So ASME says blow down is continuous or it's from a water level control, like a low water cutoff. Okay, so that's what blowdown is. Now, blow off is intermittent, and it's from the mud drum. Or base of the fire tube boiler shell, that type of thing. And they have two different purposes. Blow down, continuous, is for discharging and controlling TDS. So we have particular guidelines about what is the maximum dissolved solids concentration. If we have too much TDS, we're going to get foaming, priming, carryover, things we don't want. To prevent foaming and priming and carryover, we're going to try and keep our dissolved solids in the boiler within a prescribed control range. And if we have too little TDS, in other words, if we've got too much continuous blowdown going on, then what we're going to do is we're going to waste money. So too much CBD wastes heat, it wastes chemical, it wastes material in the form of water. And because it wastes all of that stuff, it costs us money. And so what we're trying to do is run our plant economically, so just the right amount of continuous blowdown. So our water treatment rep will prescribe whatever control range we want to have for our TDS. Now, any time that we're trying to control dissolved solids, the principle is this. Here's my boiler, there's the water, it's got a lot of dissolved solids in it. Here's our feed water, it has very few dissolved solids in it. And if our TDS is too high, then we need to discharge material with a high concentration and replace it with feed water with a very low concentration. And that, my friends, is the only way we can control dissolved solids concentration. Which is really funny, because when I got into this field here, I started working at the Pan Am swimming pool in Winnipeg. And I was working in the maintenance department, and so we had pool water, and we would test the pool water for dissolved solids, and we would always be blowing off a certain amount of pool water and making up with relatively pure water. And then when I got into power engineering and I'm learning about dissolved solids in the boiler, I went, oh, that's the same principle. Okay, so you should know that the only way we can reduce dissolved solids is to get rid of the stuff with high solids and replace it with low solids. We can't miraculously make the solids disappear. Now, how pure is the water going in? If we have super pure water, we're going to blow off very little. Because it's going to take it a while for the dissolved solids to concentrate, to reach a particular level when we're going to be concerned about operating our continuous blow-off. or blowdown, I should say. Whereas if we've got water going in, that, you know, it's pure but not that pure. We'll just say pure. Okay, it's got a little bit more dissolved solids in it. Then what we're going to have is a little bit more blow off, or blow down, I should say. Oh, you know, I'm confusing. I told you guys what the term, and I keep confusing them. Blow down. And I'll tell you why I keep confusing the two terms, blow down and blow off, is because when I was studying this stuff, the terms were used indiscriminately by my teachers. And here I'm doing the same thing. So we can then determine the percent blowdown based upon the quantity of blowdown water and divide that by the quantity of, probably should say makeup water. Or you can say feed water, I guess. Yeah, let's say feed water. That's a better way of looking at it. Feed water. So ignore my thing there. So we can put a meter here. And we can meter the feed water in. And we can put a meter here on the blowdown. And if we know how much is being blown down, we divide that by the amount of feed water, and that gives us our percentage blowdown. Problem is, we usually never have a meter there. So we'll have to find some other way to determine percent blowdown, and there are other ways we can do that. Okay, so where do we stick the continuous blowdown pipe? Here's our boiler water level. Within the top 6 inches or so of the boiler water level, that's where we get the most TDS. And I actually worked with a guy who, on his shift, if he was trying to lower the TDS, he would actually change the boiler water level because he knew the position of the continuous blowdown pipe, and he would actually, you know, lower or raise the water level in the boiler, the set point, so that he knew that he was maximizing the dissolved solids concentration being discharged, and that way he could actually discharge less water and chemical and discharge more of the dissolved solids. So he was a little bit wacky, but he was a very good engineer, I tell you. So usually we see the continuous blowdown pipe somewhere within that top 6 inches or so of the boiler water level. And what is 6 inches? 6 times 25. You get the idea. You can turn that into millimeters if you think in millimeters. Now we also have a feed water line here. And notice that there's a pretty good distance between the CBD pipe and the internal feed pipe. What would happen if they were right side by side? We've got pure feed water coming in, or relatively pure feed water. And I got my CBD, if it's right beside it, is discharging to waste. So why would this be a bad situation?
And then you're just discharging feed water.
Bingo. Yeah. We don't want to get rid of our nice clean feed water. So now then we also usually have a chemical feed line to feed drums, feed chemical directly into the drum, and we usually put that somewhere nearby the feed water. So this here will be chemical feed. And again, for the same reason, we want to maintain a pretty good distance between the CBD pipe and the chemical feed line, because we don't want to be dumping chemicals that are unconsumed, unused. So if you take a look at the basic system, we've got a continuous blowdown. That would be our isolation valve, followed by some sort of a metering valve, like a needle valve, with a special set of graduations on it, so we can actually see what its opening is and we can adjust it. So a micro-adjusting needle valve. And as for the intermittent blow-off from the mud drum, we're going to have the two valves that are required by ASME code. Anyway, they're both going to discharge into our blowdown tank, or sometimes we call it a blow-off tank at the same time, or it's the same terminology, I should say, blow-off tank, or sometimes we call it a blow-off vessel. You'll hear all those terms used. And because this stuff here is high pressure, let's say it's at 2 megapascals. Inside the blow-off tank, it's atmospheric pressure because it's vented to the atmosphere. And so what's immediately going to happen is once that water gets into that tank, it's going to flash into steam. So we're going to see steam going out that way, and the steam is going to carry away heat, latent heat. So steam and heat are going out. So in other words, we're wasting materials, we're wasting water, okay, that we got to treat for the makeup now, because we're losing water, and we're also losing heat. So then the water that goes to the sewer also has heat in it. And so though this is a very simple and very common system, it is wasteful of materials, it's wasteful of money, it's wasteful of heat. So this one here is a little bit better. And if you work in a plant that does not have a continuous blowdown heat recovery system, you can be a real keener and design something and size it up and present it to the chief engineer. Sort of do a cost-benefit analysis, and you could be a real keener, you could be a rising star in the power plant. So let's see how that works. Here is our CBD collecting pipe. It's inside the steam drum. It's a perforated pipe along its entire length. And then we're going to take that CBD, the high TDS water. There's our valve required by code, the isolation valve. And then we're going to take it down this way. Another isolation valve. And here is our micro-adjusting CBD valve. Now, because the CBD is running almost continuously, it's a good place for us to take a sample as well. So we're going to have a sample cooler on there as well. But anyway, after the CBD water hits the flash tank, that flash steam and that flash and the heat that it carries, so the materials and the heat get carried to the deaerator. So the deaerator might be operating at 100 kPa gauge pressure, and the steam drum might be at 2000 kPa gauge. And so what we're doing then is we're operating the flash tank at 100 kPa, and the flash steam, the materials and the heat basically are going to the deaerator. So we're covering materials and we're covering the heat, and we want that heat for heating up the water in the deaerator anyway. Now, of course, this is pure steam. It doesn't have impurities in it. The impurities get left behind in the base of the flash tank. So we're not actually recovering dissolved solids. We're only recovering pure water and heat. This has got a simple float control, and so when the water level in the flash tank goes up a little bit, it's going to discharge that hot water into a heat exchanger, and ultimately, it says blow down to sewer, but what we'll do is we'll put it into a blow-off vessel. Now, but it's still hot, and we want to recover that heat, So what if we take our makeup water and put it through a heat exchanger, pick up that heat, so all of the makeup water that's going to the deaerator and into the system is also picking up heat. So very, very good type of system. We can be saving tens and thousands of dollars a year. But the problem with this is the continuous blowdown valve, this one right over here, manual valve, and so the operator has to change the setting on the valve based upon water treatment tests on an ongoing basis. So let's say Jill comes on shift and she takes a look and the water level of TDS is too high. And she goes, oh, I got to open up the continuous blowdown valve. So she opens it up a little bit and she records the new setting and whatever the TDS was when she opened up the valve. And then she has a shitty day at work. Everything's, alarms are going off, and then all of these, maintenance people show up unannounced, and she didn't know she's got to issue work permits and blah, blah, blah. And at the end of her day, she forgets to retest the TDS and close the CBD valve. So Brett comes in, and he's her relief, and he tests it and goes, oh, my dissolved solids are too low. So what does he do? He closes the CBD valve back a little bit, or maybe shuts it all off altogether, and he wants the cycles of concentration to once again get back into the normal dissolved solids range. But he falls asleep on night shift, and he forgets to do the test. And he forgets to open up the valve, and then Jill comes in the morning and she's all pissed off because the TDS is way too high again, and how come every time she comes on shift the TDS is too high? And this is this vicious circle, vicious circle of TDS going up and down and up and down and up and down. Why? Because it's still up to the operator to control the setting of the CBD valve. And sometimes people screw up, sometimes people forget, and sometimes people have really big days, and lots of reasons for that to happen. So we can get, with this system, deviations in the dissolved solids. So ideally, if there was a way that we could monitor the dissolved solids concentration on a regular basis, and automatically adjust a micro-adjusting control valve to control and maintain the DS of the water constant, we can do that. Now, then what we have is a very stable TDS, and maybe we could even save more money in the operation of our plant. So, how do we figure out the TDS of the boiler water? Well, typically in a plant we use a dissolved solids meter, which is really a conductivity meter. And what we find is that as TDS increases, conductivity also increases. Something like that. So we get high TDS, we get a high water conductivity and go, oh, our TDS is too high. So we close the CBD valve a little bit, we open up the CBD valve, and then our TDS falls down. Maybe it falls down to there, okay? And then when we test the water again, we find the conductivity is a little bit lower. So what this means for this system to work continuously, we must have a continuous flow of boiler water through the sensing device. So here's our CBD line. Here's our automatic micro-adjusting boiler blowdown valve. And we've got this sample line here going through a sample cooler, because if it's really hot water, it'll wreck our sensor. And then here is our conductivity measurement, a primary sensing element, and it's going to send a signal to our blow-down conductivity controller. And so we're going to have a conductivity set point. It's going to compare the blow-off water or blow-down water conductivity to the conductivity set point. It's going to give you an error signal, which is our control output signal, is going to go to this blow-down control valve and control the amount of blowdown. Sounds wonderful, but what it means is, number one, you must always have a flow of water past the conductivity measuring cell. Okay. Otherwise, it's just going to be measuring stagnant water. One of the drawbacks of this system. Then the next drawback of this system is the conductivity is not a great way to determine dissolved solids. Yes, there's a relationship between dissolved solids and conductivity, but it's not a perfect relationship. So if you got stuff in there like chloride ions, chloride ions are very highly conductive. They have a disproportionate effect on conductivity. They've got a greater effect on conductivity than some other dissolved solids and purities. So it's not a straight line relationship. It's not a perfect relationship between dissolved solids and conductivity. So, but it is kind of like what's the word I'm looking for? It's like the best we got. Okay. Now I think that we have this in boiler 1 and boiler 2, and you won't be surprised by me telling you that it doesn't work. So there's another thing. We start to rely too much on instrumentation, and we get something that doesn't work, and we end up just doing it manually anyway. And by the way, there's no reason we cannot be flashing that blowdown water and recovering the heat to the deaerator and using like a blowdown water heat exchanger as well to be transferring heat to the makeup water. So we can combine this with that. And there's our blowdown. So the next is about the samples and tests and monitoring equipment. So first, let's take a look at a part per million. This is one of the methods we use to report concentrations of whatever it is in the water that we want to report on. So for example, if we've got OH ions and we want to report our hydroxyl ions, we can express that in parts per million. If we've got sodium sulfite in the boiler water, we can report its concentration again in parts per million. So what does it mean? If I've got 1 kilogram of, let's say, Na2SO3, and I've got that dissolved in 1,000,000 kilograms of water, then what I have is 1 ppm of sodium sulfite. Makes sense, right? Now, nowadays, there are a lot of reports that are moving away from parts per million, and they're expressing concentrations of impurities, dissolved solids, that sort of thing, in milligrams per liter. So what the heck is a milligram per liter? It's basically a part per million. Okay, these are equivalent things, as long as we're not talking about a super concentrated solution. If our solution is primarily water, okay, overwhelmingly water, so we can talk about 30 parts per million or 50 parts per million, then what was water has a particular density. So let's take a look here. Let's say I got a part per million, which means I got a kilogram per million kilograms. And here's where the density comes in. So the density of what is overwhelmingly water, okay, relatively pure water, we're just going to say it's 1,000 kilograms per cubic meter. So what have we done? We now have got kilograms per cubic meter. But what we want to get is milligrams per liter. So we know that 1 cubic meter has 1,000 liters in it. So now we've got kilograms, 1,000 kilograms per 1,000 liters. And we know that a kilogram is 1,000,000 milligrams. So it's just simple dimensional analysis, and then what we're left with is milligrams in the numerator, liters in the denominator, and the thousands cancel out, and the millions cancel out. And so then there's your evidence, right? There's your proof that 1 part per million is 1 milligram per liter. So don't be confuzzled when your water treatment report comes back and you're expecting it to be in parts per million and they're giving you milligrams per liter. Now, we have a whole bunch of tests that we take on boiler water. So this is a boiler water test, phosphate test. We also do a sulfite test on boiler water, if sulfite happens to be our oxygen scavenger. And we're also going to do a P&M alkalinity test on our boiler water. So let's first of all take a look at the phosphate test. This is different than the one that we do at the Synovus building, but this is what we call a color comparator. And really it is the same test that we do at the Synovus building, but we don't have the fancy electronic gizmo here that's determining the parts per million of phosphate. And we want there to be phosphate because that is going to get rid of the calcium and magnesium scale-forming compounds through precipitation. So we always want to have a certain residual of, let's say, 30 to 50 parts per million, somewhere in that range. So we take a boiler water sample, we cool it, we filter it, and we add the various reagents, and the bottom line is this: every time you are doing a test like this, you follow the test procedure that's in your plant. And it will be provided by a water treatment rep. And so now what we're going to do is we're going to take one is our control sample, and the other one is going to be the one where we're actually going to see color change. And we're going to put this slide in here. I don't know if anybody here has seen a ViewMaster, but it's kind of like a ViewMaster. And then what we're going to do is rotate this thing one way or the other until we can cause the color of the sample to match the color that we see. So here's a really light blue, which means 2.5 parts per million. Medium blue is 25 parts per million, and dark blue 50 parts per million. And there you go. If we find that we're a little bit low, we can add phosphate. Now, then, actually, if we are high, then usually we don't do anything. What we do is we wait, and because phosphate is consumed, okay, anytime magnesium or calcium gets into that boiler water, they are going to consume phosphate. So we just wait a little bit. Oh, we got 70 parts per million in the boiler. That's well, let's wait a week, and then over that week period, we'll see that the phosphate residual drops. And then as for the sulfite test, if we are adding Na2SO3 as an oxygen scavenger, we'll want to make sure that there's always some of this residual available. And so what we're going to do is we're going to test for this ion, the SO3 ion. And we know that that ion, when we've encountered dissolved oxygen, it's going to form SO4. So we're going to take a boiler water sample. Very important that we keep this sample from contacting oxygen. So if I have a sample bottle that's that big, I'm going to fill it up right to the brim till it's overflowing, and then I'm going to cap it up tight so that oxygen can't get in. If oxygen gets in, it's going to screw up our test result. Then what we do is we add an acid-starch indicator, or maybe what we'll do is we'll add phenolphthalein, then we'll add acid, and then we add the starch indicator. The reason that we have to do this is to adjust the pH of the sample, and we do that with acid. Sometimes the acid and the starch are built into one single chemical. So for example, right here you can see that that label says acid starch. Okay, that's acid starch indicator right there. And then we're going to titrate it with potassium iodide iodate until we get samples persistently blue. And so here you can see it's starting to turn blue. And then we reach the end point when the whole thing is blue. And then we measure how much potassium iodide iodate we added. We apply some kind of a multiplication factor for the sample size. So, you know, did you use a 50 ml sample? Did you take a 100 ml sample? You know, how big was your graduated cylinder? So there'll be some sort of a multiplication factor for the size of your sample, and then we report it as milligrams per liter. Now, the P&M alkalinity is probably the most important test you're going to do, and you're going to do it so many times that you're going to be able to do this blindfolded. So we take a boiler water sample, we add phenolphthalein, and the sample turns red when there is alkalinity. If the water has zero alkalinity, it does not change color. It stays clear. What is alkalinity? Bicarbonate, carbonate, and hydroxyl. So one thing that we need to know is the OH alkalinity and HCO3 alkalinity do not coexist. Because what happens is this little hydrogen decides to scoot over there and form H2O. So what we end up with is carbonate alkalinity. Okay? So we never get bicarbonate and hydroxyl at the same time. So let's say we added phenolphthalein, it turns pink, we know that there's alkalinity. Now we've got to find out what kind of alkalinity, so we're going to titrate it with sulfuric acid. So I fill up my auto burette here all the way, and I start adding dropwise until that pink sample turns clear, which is the end point, which has a pH of 8.3. At that point, all OH is neutralized by the sulfuric acid, and 1/2 of the CO3 2- is neutralized. So then what we're going to do is, then we record how many milliliters of titrant we have added. That is our P-alk. Then what we do is we add some sort of a methyl. There's all kinds of methyl, orange, green, purple, something like that, and really depends who you're talking to and what they call the stuff. So if it turns green, it's the same sample, then this stuff here has more alkalinity. If it immediately turns purple, then you have no alkalinity, no more alkalinity, so all of the alkalinity that you start off with was hydroxyl and carbonate. So we're going to titrate it until it gets to its endpoint, and here you can see it's going more toward its purple endpoint. And again, we record the milliliters added, and then we end up with our total alkalinity. So malc is equal to total alkalinity. By the way, this malc endpoint is 4.3 pH. So once you get to 4.3 pH, all of the alkalinity is removed. Then we do the math. OH alkalinity is 2P minus N. And if we want to know carbonate alkalinity, we can go 2M minus P. So we're going to leave it there today. And when we come back on Monday, we're going to finish off this water testing and the methods of feeding chemical into our boilers and into our systems.